right, these notes are going to cover Chapter 11, Chemical Reactions. We will start by looking at signs of chemical reactions, symbols used in chemical reactions, start looking at balancing equations, and looking at some ways that we can make balancing much easier. So the four main signs that indicate a chemical reaction has taken place are things that we've already looked at in Chapter 2. The first one is the formation of a precipitate. We actually did the precipitate lab in Chapter 7. Remember, that's when two aqueous solutions combine to make a solid. You will know that it's a solid because there's a change in the color. You may also recognize that a chemical reaction has taken place if there's a change in odor, production of a gas, and transfer of energy. So input or release of light, right? Sound. Those are all things that we can look at. When it comes to chemical equations, a chemical equation is a representation of a chemical reaction, and we always have reactions in which the reactants are on the left, products are on the right. So reactants is the substances that are present at the start, and products, the substances that are produced in a chemical reaction. So reactants are on the left, products are on the right. You gotta know that for the test, okay? So I would TQ that. So reactants are on the left, products are on the right. When it comes to a chemical equation, right, it is a representation of a chemical reaction, which we already saw a little bit ago. We may use a catalyst. It is a substance that speeds up the reaction, but it is not used in the reaction. A couple of symbols that we use to represent chemical equations: the addition sign can be used to separate two reactants or two products. The arrow means yield, separates reactants from the products. You can have the double-sided arrow, which means a reversible reaction, or you could also have this, right? Just arrow to the left, arrow to the right. S for solid, L for liquid, G for gas. AQ designates an aqueous solution. But what it really means, right, is that the substance is dissolved in water. I would also know that one for the test. If I want to represent that heat was used in a reaction, I'm going to use a triangle or the word heat above, right, the actual arrow, the yield sign. If I put an arrow in the reaction and I put a formula written above, right, that's going to indicate that a catalyst is used. So if I put PT above the arrow, then that's going to show, right, that a catalyst was used. In this example, specifically platinum. In this example. Why? Because PT is a symbol for platinum. So let's look at another example. Show that nickel was used as a catalyst in the following reaction. So I want to show that nickel, right? Nickel has the chemical formula Ni, and what we do is we write it above the arrow. So I'm going to put Ni, and then that is above the arrow, and that is my catalyst. The reason why we don't want to put it on the left side or on the right side is because, once again, it's not used up. And so because it's not used up, it's not fair to represent it as a reactant or a product. The next concept is the law of conservation of mass. In a chemical change, mass cannot be created or destroyed. I would also know that for the test. Okay. all chemical reactions, so if your word all was hole punched out, right? All chemical reactions, so it must be balanced to obey the law of conservation of mass. So the law of conservation of mass states that all chemical reactions must be balanced. To obey the law of conservation of mass, atoms can only be rearranged. I would also know that for the test. All right, now we move on to page 2. So when it comes to balancing, right, there's a couple of things that we can look at to make it easier. The first thing that we have to know is that we have the right formulas. This is going to be a big deal when we look at word equations tomorrow. If you don't recognize your diatomics, you don't recognize your acids, or you don't recognize your polyatomics, right? It's going to be difficult to get the right formula. And if you don't have the right formula, you're not going to be able to balance correctly. So always make sure that you have the right formulas first. But if I give them to you, you don't have to worry about that, which will be true for tonight's homework. I give you the formulas. Then you're going to take an atom inventory. I'm going to show you how to do that. You're going to balance the atoms by changing the coefficients. So what that means is that I can only change the number that's in front of the actual substance in the chemical reaction. Now, we're going to start with the atoms that appear only once on each side. Usually we're going to keep hydrogen and oxygen last. And the reason why we keep hydrogen and oxygen last is because they're diatomics. And because they have a 2 after them, right? It's just going to make it harder to balance them right away. All right? If it's a polyatomic ion, so remember I gave you a list of your polyatomics. It looks like this. Okay? This list is going to help us because if it's a polyatomic on both sides, we're going to treat it as one unit and balance it as a single unit. Okay? Other balancing tricks, if you're having trouble getting it to balance, double the first compound and try again. A trick for H2O is to write it as HOH, but only if the reaction does not contain a hydrocarbon. We'll talk about that. But to balance hydrocarbons, a general rule is that if there's an even number of carbons, double the hydrocarbon and then balance. So we're going to see that strategy, and then double check to make sure that all atoms and ions are balanced and the coefficients are in the lowest possible ratio. So let's look at rules 2 and 3. Take an atom inventory and make sure that we only change coefficients. So what I like to do is I like to put a line, right, that separates the left side from the right side. Remember, we have reactants on the left, products on the right. So I look at what elements I have. I have H and I have O. So I have H, O. And then I write straight across those exact same element symbols, H and O. All right? Now, what I want to do is do an atom inventory, which means I keep track of what atoms I have and how many. So I have H and O. How many H's do I have? The 2 here means that there's 2 of them. There's nothing here. 1 is understood. 1 times 2 is 2. Oxygen, 1 times 2 is 2. On the right side, this 2 after the H means there's 2 H's. 1 is understood, but I can write it out if I want, right? There's only 1 oxygen. Don't tell me 0. If it were 0, we just wouldn't put anything there. So right now, I can see that my hydrogens are balanced, my oxygens are not. What is important is I can only change the numbers here. After I change the numbers here, that's going to change the numbers down here. So right now the oxygen isn't balanced, so I need 2. So I ask myself, 1 times what gives me 2? 2. But notice, when I put a 2 here, that's going to change everything after. It's going to change H and O. So what I like to do is I like to cross out the H and the O, and put an arrow, because what that means is I cannot look at these numbers anymore. What I do is I cover them up, right? And I go back to the balanced equation or balancing equation, right? And figure out how much I have. So 2 times 2, now the H is 4. 2 times 1, now the O is 2. So I did that work and now my O's are okay. But now my H's are not okay. So then I ask myself up here, right? I'm going to cross out the H. And I need to fix that, right? I need 4. So then I look up here. I don't look down here, so I look up here. I need 4. What times 2 will give me 4? 2. That changes my H. Now I have 4. Now that my hydrogens are equal, 4 and 4, oxygens are equal, 2 and 2, I'm done. So last thing I do is always double check that the coefficients are in lowest terms. 2, 1 is understood. You don't have to put the 1, but when we grade, I would say that this is 2, 1, arrow, 2 for the answer. So this is what taking an atom inventory involves. You're going to write the element, all the elements or units that you're going to use to balance, and then, right, track your atoms as you are changing the coefficients. Okay, now we're looking at rules 5 and 6. If a polyatomic ion is present on both sides, treat it as a single unit. And then 6b, write H2O as HOH. Okay, so number 5, right, is that I'm going to keep polyatomic ions together. And 6 is that I'm going to write H2O as HOH. Now, this is where you got to be careful. Writing H2O as HOH, you should only do that. You should only do that if you have OH over here. If I don't have OH over here, there's no point in separating it, okay, into HOH. So what that does is it helps me to see that OH is a group on both sides. So why did I do that? Because now you can see that hydroxide is one of my polyatomics, so I want to keep that together. Do I have any other polyatomics? Yes. I have SO4. So I'm going to keep those together. So I like to also just kind of do a notation around them. So I circle this one, they're the same, right? And maybe I'll box this one and that OH. Okay? So now I do my atom inventory, atom/polyatomic inventory, because I'm going to keep those units together. So I have H because that's separate. I'm going to keep my SO4 together. So I have my SO4. Then I have Na. And then I have OH. Remember, the atom inventory works as long as I keep them straight across, the same amounts. So I have my H, SO4, Na, and my OH. So now, I look at my equation. How many H's do I have? 2. And you might say, but what about this H? Remember, we're keeping this together over here. So how many H's do I have? Just 2. How many SO4s? Don't tell me 4. SO4, we've decided to group together. OH is grouped together. So there's only one SO4, not 4. NA's 1, OH 1. Over on this side, how many H's do I have? Remember, this H is by itself, this OH is grouped here, so I only have one OH. SO4, I have only one. Na, there's a 2 there. OH, there's 1. So now I need to balance. And remember, number 4 says try to keep H and O last. So I'm going to do that. So I don't want to start with the H, stay away from the O, so let's look at Na. The Na is 1 here, 2 here. So I need to change them so that they're equal. There's 2 here, so I want to get 2 here. So what I'm going to do, right, is change this one here. And I want a total of 2, and so I'm going to put a 2 here. But that's going to change Na and OH. As soon as you put a number here, cross out the substances that are after it. So I cross off the Na and the OH. And I don't look here anymore. So that's why I put the arrow. That means don't look there anymore, right? I look up here. Now I have 2 Nas, 2 OHs. So I did that work. Now my Nas are balanced, but now my H and OHs aren't balanced. But I can go ahead and work with my OH. 2 here, 1 here. So what do I need here for them to balance? I'm going to put a 2. The 2, though, changes everything after it. So it changes the H and the OH. So I cross this out, look back at the reaction. So now, don't look here, look over here. 2 times 1 here is 2. 2 times 1 OH, right, is also 2. So 2, 2, 1, 1, 2, 2, 2, 2. They're all balanced. So remember, now let's see if they're in lowest terms. 1 is understood. I can leave it blank or put a 1. So 1, 2, arrow, 1, 2. Can 1, 2, arrow, 1, 2 be reduced by dividing them by a smaller number and still have whole numbers? No. So that's balanced. Rule 6A and C now is what we're going to look at. For 6A, it says, if you're having trouble getting it to balance, double the first compound and try again. C says that if you have an even number of carbons, double the hydrocarbon. What do we mean by that? Okay, if I have an even number of carbons, that's 6C, sorry. So I'm going to look at that one, right? If I have an even number of carbons, do I have an even number of carbons here? Yes. And so the trick is, if this were 1 or 5 or 7, I wouldn't want to do this trick. But because it says, do I have an even number of carbons in a hydrocarbon? A hydrocarbon is a substance that has hydrogen and carbon. This has hydrogen and carbon. Because there's a 2 there, it helps to double the hydrocarbon. So what I'm going to do there is double that first before I even do an atom inventory. It's just going to help us out. So I'm going to do my atom inventory. Elements that I have, C, H, O. Same elements here, C, H, O. Now you might say, here's H2O, right? Should I separate H2O into HOH? Well, remember, I don't want to separate H2O into HOH unless there's OH on the left side. So should I separate this H2O into HOH? No. And the reason why is because there's no OH like there is in this one on the left side. So now I'm going to do my atom inventory. Carbon is 2 times 2 is 4. Hydrogen 2 times 6 is 12. Oxygen 1, 2. Over here, carbon 1. Hydrogen 2. Now you got to be careful with oxygen. Be careful with oxygen. So I'm going to use a different color. Notice how oxygen, right? Oxygen is not only in this one, but it's also in this one. So you got to be careful because you got to track it in 2 spots. 2 plus 1 is 3. A little thing I like to look at is if I have a hydrocarbon with oxygen, it's always going to form CO2 and H2O, and these numbers are always going to be 1, 2, 3. 1 carbon, 2 hydrogens, 3 oxygens. But now let's work to balance this. Remember, we're going to try to keep H and O last. So now my carbon, 4, 1, so I'm going to put a 4 here. Now, remember, that's going to change everything after it, C and O. So I cross out C, cross out O. You go ahead and figure out what it is. Go ahead and pause the video and then restart when you're ready to look at it again. All right, so I'm ready to look at it again. Here, carbon, there's 1 here, so 4 times 1 is 4. My oxygen, 4 times 2 is 8, but don't forget to add this 1 oxygen. That's 9. All right, now I move on to my H's. I like to just go in alphabetical order after I've balanced my carbons, so H is next, then O. Another reason why I want to keep O last is because it's in 2 spots. So now I start with my hydrogen. I have 12 here, 2 here. So I ask myself, how can I get 12? So I don't look at this number, cross that out. I need to get a total of 12. 2 times what gives me 12? 6. When I do that, that's going to change H and O. So I also have to cross out the O. Hydrogen now is 6 times 2 is 12. Oxygen, 6 times the 1 here is 6, plus 4 times 2 is 8. 8 plus 6 is 14. What a lot of students do is they say, oh, let me change this at 6. Let me go ahead and just add 6 to this 9. You can't do that. Take the time to just look back at the coefficients in the balanced equation. So now, the last thing I have to balance is oxygen. I need a total of 14. Cross this out, right? 2 times what gives me 14? 7. So that gives me 14. I'm done balancing because 4 equals 4, 12, 12, 14, 14. Last thing I check, are these in lowest terms? 2, 7, 4, 6. Yes, I can't divide those numbers and get a smaller whole number. Rule 7, I cannot stress enough, right? You have to make sure that they're in lowest terms. So what if I got 4, 2, 4? Those are all divisible by 2. So I'd have to take the time to simplify that. I can divide all these by 2. So it'd be 2, 1, 2 for the coefficients. All right? So this completes the actual notes for today. But now what we want to do is look at what our homework is. So our homework involves us looking at the homework packet. So we have here our homework packet. You are going to do problems on 11-1. So 11-1 looks like this. You're only going to do 1 through 10 on here. So 1 through 10. Don't worry about this side here. You must do an atom inventory. So for the first day, right, you must include atom inventory for problems 1 through 10. Remember, you can use this strategies that we talked about on page 2 of the notes. That's going to help you a lot. If you feel that you don't have enough space to do your atom inventory, please do it on a separate sheet of paper, and then upload if you have to upload, right, to show that work for credit. Okay, so once again, 1 through 10, first page, only these 10 problems with an atom inventory. Please disregard this 3 here. It's not supposed to be there. On number 10, there was an extra 3. Thank you.